Right, let's get into this. The function nt is given as follow, and understand that n is in thousands, so take note of that. And the initial deer population is when t equals 0, so n0 calculate this will be 1, so therefore there were 1000 deers initially. So this is the number of deers we have on the 1st of January 2004. Now in the second part, given that the deer population rose to 2,490, so 2490 is equivalent to 2.49 thousand, right? So means that we will let n be 2.49 and time as 2 because after 2 years. So our job is to show that k is 0.8. It will be approximately 0.8 I suppose. And so we start with this. So we have n2 equal to 2.49. So this left hand side would be 4. We have 2k is 2.49, or in other words 2.49 here is 1 plus 3 power 2k. So just do the usual algebra. You need to be careful with this. You get this 1/3 4 over 2.49 minus 1, and I'm taking ln both sides. Okay, and so therefore I can write like this, and this is just ln e this is 1, ln e is 1, so that means k is negative half ln 1/3 4 over 2.49 minus 1. So now we get the calculator, right? Get a calculator and enter this. I've calculated this actually. Negative here, and ln 1/3 and the parenthesis so we'll get 0.799 for k. So approximately 0.799. Of course, this is equal to 0.800 if we round to 3 significant figures. So we have shown that k is 0.8 after 2 years with the number of n given. Now move on to here. Now how long would it take for deer population to double its original value? And we need to find the month and year that this population is achieved. And initially we had 1000, so we do not know when, but nt, when would this happen, right? 2000. So it means they ask you to find the time. We already know the value of k, so we just let it be. 2000, but it's not 2000, right? I made a mistake. It should be 2 because annual is just 1, so it should be just 2. And if you work on your calculation, you get this equivalent to 1 eventually. Okay, just do the usual calculation, the algebra, and you end up with this e 1/3. Taking ln both sides, you end up with this t ln e, so ln 1/3. Okay, so in this here we're actually taking ln to both sides, and this is just 1, so therefore t is right, if you calculate this, this is approximately 1.37 years, but 1.37 years is 1.37 years. The part is this decimal part, so 0.37 times 12 months is roughly 4.4 months. So it's about 4.4 months. Is more than 4 months. This is approximately 1 year, 4.5 months. Okay, just make more or less, right? And so that means the month and the year that this population will be achieved will be like, from the 1st of January 2004, you plus 1 year, 4.5 months, and the date will be therefore be in May 2005. So this population will be achieved in the May of 2005, right? And now this part we need to differentiate n. So n is this here, and I'm going to express it as follow, because this makes the differentiation easier. I don't want to use a quotient rule, I want to use a product rule. It's power -1, and so dn dt is -4 1 plus 3 2. Using chain rule, I will have -2.4 e to the power of this, right? And you're going to simplify this. -4 times -2.4 e to the power of -0.8 t, and this thing here I can express as follow. Because it's to the power of -2, I can express this as follow: t squared, right? Just nice. So finally I would end up with this nice little thing here. Square, and right here I'll get 4 times 2.4 is 9.6, okay, and e to the power of -0.8 t. That's nice. So this is the differentiation of and respect to time. And so as this thing, I'm going to change the color a bit here to illustrate here. This is a square of an expression, so it's always positive. 9.6 surely is always positive. And how about this? E to the power of -0.8 t. Now in any exponential function is always positive, and so this is also positive, 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 and positive. And that means your dn dt is always positive for all t, and that means that N here represents populations of deer, and DNDT means is growth. So the populations is always increasing. That's the implication of DNDT being a positive always. Alright, and moving on here, what happens to the function NT after a long period of time? Alright, this is be wary about this. E3 here, 0.8t, and again when time tends to infinity, this term here 8t is going to be really huge, right? Yeah, but when you write like this, it's going to be really big. So this is going to tend to 1 divided by a really big value. It tends to 0. So time tends to infinity, n tends to 4, 1 plus 0 equal to 4. So the population approaches 4,000 years as well, when as time tends to infinity. So I mean, after a long period of time, the number of deer would stabilizes at roughly 4,000. And lastly, how do you find this? The deer population change from increasing at an increasing rate to increasing at a decreasing rate. So that's what they're saying, is that we want to find DNDT such that it behaves like this. There's a peak of the rate of change, and then that it goes down here. So it's increasing at an increasing rate, and then it's increasing at a decreasing rate. So this is less, the rate of change is decreasing. So to do so, what we want to do is we're going to graph DNDT in our graphics calculator and find the maximum point. Okay. So we'll do this. We need to refer to the DNDT that we got in part D. Now I've already entered this here, right here, and I'm going to set up the wheel window carefully. And because we're talking about time, I know that well, X here represents time, so I can pretend doesn't matter. Okay, and where else Y here represents the population, so I can take n. 6 is okay, because we know as t tends to infinity, the number is 4, or 4,000 rather. So we are ready to sketch it. So here is it. There's a maximum, as you can see here. If you don't see, I try to get nearer to it. It's right here, and so I can use the calculator to solve for me to find the maximum. And this is 1.373. So this is the point or value of time where the deer populations change from increasing at an increasing rate to increasing at a decreasing rate to the maximum point. So I can say that from GC, the value is t equal to roughly equal to 1.37 years, and that would be our answer to these questions. So I hope you try these questions and other questions in this exam. All the best.